So hello, good morning, good evening, good afternoon, everybody, wherever we might be. It is my great pleasure to welcome our former collaborator, SUTANU Roy. You spent some time in Warsaw, if I remember correctly, working with Voronovich. I don't remember when it was, but it seems like ages ago. And now we are very happy to see him again, especially that he is going to tell us everything and more about the subject, which is very exciting for us, which is braided quantum symmetries of graph sister algebras. SUTANU, the Zoom is yours. Take it away.
Thank you, Peter, for the kind invitation. And it's always good to be back to Warsaw, virtually, of course. But yeah, you are right that I used to visit Warsaw almost once in every semester during my PhD between 2010 and 13. So twice a year at least, I think. Anyway, so yeah, so what I'm going to talk about is, I mean, the goal is to interpret braided quantum groups as symmetry of certain objects. So in this case, we are interested, I mean, for graph sister algebras. So okay, so a little bit about the history of quantum symmetry, which I'm sure, I mean, all of you know way more better than me, of course. But just to mention, just to make it self-contained. So it started with, of course, Wang's work on quantum permutation group, and then it was used to compute or to develop the theory of quantum symmetries of various finite structures. I mean, in particular, graphs, matrix spaces. And then at the same time, the idea was to see whether it can be, it is possible to actually construct quantum isometric group of spectral triple of compact type, and that was due to Goswami around 2009. But then from there, I think it was Banika and Adam. They got interested, I mean, mostly more motivated by the work of Goswami. They actually came up with a more general setting of quantum symmetry of.
I believe that regarding SUQ2, there should be Shitash instead of Shirash. But R is
sorry.
T on the keyboard.
Yeah.
You can imagine that.
Yeah. Of course, there is a mistake. Mm-hmm. So yeah, but I'm still in the non-braided setting. So yeah, so it was Adam and Banika. They came up with the notion of quantum symmetry for any sister algebra, but equipped with orthogonal filtration. But surprisingly, there was no development until 2018 on graph sister algebras. People studied quantum symmetry of graphs, but not graph sister algebras. But that was more or less done around the same time by two group of people. And so now I started working on braided quantum groups in my PhD, and then we had some nice results. But then I got interested mostly during the COVID, like, is it possible to interpret braided quantum groups as symmetry of some object? And it turns out that already Shitas and Bistron, they already had some idea, some actually nice results in this direction, but that was mostly in the mostly on the algebraic side. And then I just did some computation for matrix algebras, or direct sum of matrix algebras, more or less following Wang's work, mimicking more or less his work. And then it turns out that we got something, I mean, I managed to get something which is not classical, I mean, which is genuine braided quantum. And then motivated by that, we actually started working on graph sister algebras. And then this thing this is the analog of quantum permutation group in the braided setting. But today we are, the goal is to, the goal is to explain or basically present the results that we actually obtain in the context of graph sister algebras. So let me just briefly recall what is a braided compact quantum group. So first of all, this the notion of braided Hopf algebra, which is a very standard and well-studied notion in the context of Hopf algebras, due to started by Radford and then Majid, and I mean, there are plenty of results that is available in the context of Hopf algebras. And the idea is, okay, you actually talk about a braided quantum group, which is, I mean, Hopf algebra actually appears in the context of semi-direct product of quantum groups. So if you want to understand the semi-direct product of Hopf algebras, it turns out that one of the component is not actually a Hopf algebra, but it becomes a braided Hopf algebra, which is actually a more general object. I mean, it's a general object than a Hopf algebra. So you need some group which will play the role, which will be responsible for braiding and everything. So for today, what I'm going to stick to the circle group only. And in fact, so far all the examples of braided quantum groups that I am aware of, they are either over circle group or over circle cross integer group. So yeah, I mean, our ambient group is quite simple. It's basically circle group, and just for the sake of keeping everything quantum, I just view circle group as a compact quantum group. But it is possible to do everything. I mean, you can do everything with groups as well. So yeah. And now what we do is we actually consider the category of T C-star algebras, meaning the C-star algebras. I mean, I'm also considering unital C-star algebras also. So the objects are unital C-star algebras and equipped with a continuous action of the circle group, and morphisms are T equivariant unital star homomorphisms. So this is our category. And now if we have an action of circle group, then we can actually decompose our C-star algebra into homogeneous elements. So a homogeneous element is defined like this. So it is like if you, so X is said to be a homogeneous element of degree n if you have this, if rho of X is X times Z power n, where Z is the unitary generator for the C-star algebra CT. And then each of these spaces are closed. And then if you multiply two elements, then you actually land into the sum. And then it is also compatible, nicely compatible with the star. So if you take the star, then you get minus n. And now, most importantly, if you take the direct sum, then you actually get a norm dense. I mean, this direct sum is dense in X in norm. So this means that given this action, one can decompose the C-star algebra into nice copies, and then it is actually quite convenient to work with the homogeneous element instead of working with arbitrary elements actually. So this is something which is useful. And having that, then we actually define the monoidal structure on this category. So for that matter, the monoidal structure means we replace the ordinary tensor product, the minimal tensor product of C-star algebras, by some sort of braided tensor product or twisted tensor product. And the twisting, meaning the non-commutativity of the tensor product, is governed by the non-commutative 2 torus. For the zeta, so it is generated. So it is generated by two unitaries, and they commute up to zeta. Now, given two objects in this category, we can define these two algebra homomorphisms. So on first component, we actually put U. On the second component, we put V or VU. I mean, depending on your choice, it's up to you. And then actually on homogeneous elements, one can check that they do not commute, but they commute up to zeta power, the product of their degree. So that is on the homogeneous elements, and therefore you can actually extend this J1 and J2 to the whole algebra, and you can actually see that, okay, these two factors do not commute, pointwise do not commute. So these are the replacement of the embeddings of algebras into the tensor product in our case. And now the question is whether if we take the span of J1 X, J2 Y, whether that gives us a C-star algebra. So, and indeed that does. So before that, let me just fix a simple notation. This is quite useful to avoid things. So if we have two closed subspaces, then we actually use this notation that the product is basically the closed linear span of the of these type of elements. Now, with this notation and this this prescription J1 and J2, we actually have a very nice result. And by the way, this is actually true for so we are doing everything for circle action, but it is actually true for arbitrary quasi-triangular quantum groups or even Jeter-Drinfeld, I mean, category of Jeter-Drinfeld C-star algebras. But this is a very specific case, and this is something follows from various generalizations. So the idea is that
just a quick question.
Yes.
When you say these Jeter-Drinfeld C-star algebras, is it as in the work of Richard Nest and Christian Foch?
Yes.
Richard?
Yes.
Okay.
Yes. Yes. In the context of equivariant Poincare duality. Yes. Yeah. So yeah. Okay, so now in this particular case, this is quite simple. So this if we take the non-closed linear span of J1x and J2y, that is a C-star algebra, and this is unital. The unit element is given by the unit of this individual unit elements of this algebra. And not only that, this X box y, this braided tensor product or twisted tensor product, whatever we call it, this carry a diagonal action of the circle group, and that is also in this case, since circle group, I mean, we are viewing a classical group as a quantum group. So this is nice. I mean, this is nice in the sense there is no difficulty because this algebra is not this algebra is commutative. If it is non-commutative, then this formula actually becomes much. I mean, one has to be more careful to define this because this is clearly not well, multiplicative actually.
Sorry, so this X and this square-shaped tensor Y is a subset of what, of X tensor Y tensor the non-commutative torus, yes?
Yes, yes.
So this rho X, rho Y goes into this subset of this C-star algebra and then tensored by C
with
of
C of T.
T,
yes.
Which is classical. Okay.
Yes. But in this case, as I said, like since this is, I mean, we are working with circle groups, so there is no need to view it as coaction. I mean, in the Hopf algebraic setting, but I'm just doing it because for if you replace CT by any quantum group, the same type of result holds true because of that, just to match with the existing dictionary. So yeah, so this twisted tensor product or braided tensor product is an object in this category, and therefore we can talk about iterative tensor like X box, Y box, Z. And then it turns out that they are co-associative and so on and so forth as expected. So we actually get a monoidal product on this category. And okay, so now braided quantum group means braided compact quantum group means a compact quantum group if you define in this category. So you just take the definition by Voronovich and then just replace ordinary tensors by this braided tensor. And just you declare that to be the definition of your braided compact quantum group. So just by that, we actually can say something. I mean, we can define what is a braided compact quantum group. The only additional data here is that you have to have an action. So your C-star algebra should carry an action of the circle group so that your algebra is an object, becomes an object in this category. Otherwise, you cannot say this. So this is an extra data. And so this means that this pair is an object. It's a C-star in this category. Therefore, you can talk about braided tensor product. And then you say, okay, you say this is a braided compact quantum group if there exists a co-multiplication map, which is co-associative and it satisfies the cancellation property.
Sorry, SUTANU, I'm slightly confused. This row of CG means the coaction of C of T.
Yes.
Okay. I would put C of T here, but okay, at least I know what you mean. Okay.
Yeah. So, yeah.
Because
so the reason
when you write it this way, C of G is already part of the game. So it's always what you're referring to. But if you don't look at this comment later on, like over T or T sister algebra, T doesn't appear in the symbol. It's not part of a triple.
But that is.
I would rather decorate it with a torus, but okay, it's just a matter of taste.
Probably one should write simply rho of with superscript G.
Yes, exactly. That's exactly how I would do it. Yes.
Yeah, the reason, okay, I agree. But the reason why we actually put the C of G, because if I just, in the previous convention slide, I mean,
yes.
X was our algebra and then we put X here because of that.
I've got you, yes.
So because of that, but yeah, you're right.
Yeah.
So yeah. And okay, so this is the definition of a compact quantum group. And so basically what you can, there is another way of actually motivating this notion of braided quantum group, which there is a question, I'm sorry.
Yes, I could.
Yes.
I have a question. Is this braided compact quantum group related somehow to braided quantum group of Majid?
Yes.
Only for the torus section?
Yes, actually, yes, in a sense. I mean, not in a sense. Actually, the thing is, for torus action, this is pretty easy because you can use this action and then using this zeta. Actually, this zeta corresponds to a bicharacter on Z. So if you have an action of T, then using this zeta, you can define an action of Z. So essentially, your CG, this C-star algebra, that is actually a Z-graded Z C-star algebra. And then you are in the purely algebraic picture, in the algebraic setting. And then you can if there exists a dense star subalgebra inside CG, then you can actually talk about a braided half algebra. Yes. So yeah, in this case, yes. And by the way, just since you since you asked, so yesterday I saw an article on Archive by Neshviev and his student Eric Haberstadt. So they basically used the transmutation process by Majid, and actually they showed that the quantum group that, so I'm going to discuss at least present two examples of braided quantum groups. They can be constructed by transmutation process as well, but not directly. They have to modify the transmutation process for compact matrix quantum group, and then applying that, one can actually construct these objects as well. So this was something they did it, but that is again for, so this transmutation with respect to an abelian subgroup, actually, not in full generality, what actually Majid has in the algebraic setting. So yeah.
Thank you very much.
Yeah. And one more comment is one way to, it's a very, if you want to, motivate these braided quantum groups in a more non-commutative way, then this is basically saying that, okay, if you have a compact quantum group whose underlying C-star algebra is non-commutative, then that you can say it is actually inner non-commutative. But if you replace the tensor, but still in the definition of compact quantum group, you use the tensor product, minimal tensor product. But if you replace the minimal tensor product by this braided tensor product, that means you are actually putting another non-commutativity in the whole business. So that corresponds to outer non-commutativity, and this is something what I read in one of the articles by Majid. And yeah, so then you can actually have two types of non-commutativity in the context of braided quantum groups, and then you can say, okay, whether something is inner non-commutative, inner commutative, outer non-commutative. All four possibilities you can actually talk about. But that is just a side remark. But yes, the reason is this outer non-commutativity, because this braided tensor product is an external data in a sense. It is not something internal. So you need some external, group to act, or in this case group, but external object to act. And that is actually, in this context, this is done by the circle group. So yeah. And and of course, once we have the notion of braided quantum group, then the next thing is what are the representations. So yeah, it's the representation is, this definition is probably expected, because what you want. So everywhere you are actually, you have an action of the circle group. So if you want to represent your braided compact quantum group on a Hilbert space, then you want the circle group to act first on the Hilbert space, and then you say, okay, U is a representation of G on H. If U is actually a morphism in this category, which means that U is invariant under the action of diagonal action of the tensor product, actually under the action of the circle group on compact operators and CG, and then you have the this standard description that you want to have a representation, that identity tensor delta of U should be U1 to U13.
So yes. Sorry, so where this capital U appears in this definition?
So capital U is the representation of the circle group on H, yes, and small u is the representation of G on H.
Okay.
The quantum group.
In these two conditions, I cannot see this capital U. It should be somewhere hidden, yes?
Yeah, so basically, yes, you are right. So this capital U is the representation of T on H, which induce an action of the circle group on compact operator, and that is rho of KH.
So this invariance, okay, this invariance is
yes, and this is basically defined by, yeah, this is defined by the adjoint of U, by U star.
So Adam, you are absolutely right. I mean, this is hidden here. Yeah.
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 So yeah. And one more comment is that, I mean, in this case, because we are working with braided, in the braided situation, so why ordinary tensor? Why not twisted tensor here, for instance? That is actually I mean, one may ask. And the reason why we actually put ordinary tensor, because the action of the circle group on compact operators is inner. So this twisted tensor product can be identified with the ordinary tensor product, that can be shown. So as a sister algebra, so you just make this identification and then you choose your representation to be an element here, just to make life simpler. So okay.
Yeah, that's now, very important thing is there are many smash products which are isomorphic to the usual commutative tensor.
Yes.
Products. And this is some homological condition that what gives is I don't know, boundary or something. I mean, yeah, that's exactly how it happens. And so you say that when it's inner, then it's always isomorphic to the usual tensor product.
Yeah.
Okay.
Yeah. And also, I mean, as far as representations are concerned, we are also going to work with finite dimensional ones. So this identification becomes more easier in that sense, simpler. Anyway, so okay. Now, okay. So now let me just present one example which has nothing to do with today's talk, but just to motivate, because this example is, I mean, in the ordinary compact quantum group setting, this example is actually an arch type, the braided SUQ2. So it's actually, so the SUQ2 was defined by Voronovich for real Q, but if you replace Q by, if you take Q to be a complex deformation parameter, what happens? And then it turns out you get actually something. So the sister algebra, there is no problem with the sister algebra. The problem is with the co-multiplication map that you have for Q real. So that map doesn't exist anymore. So you have to replace this by this braided tensor. So it is, the definition is exactly the same thing. I mean, the only change is that you choose Q to be complex, and then you actually say, you claim, I mean, you actually define, consider the sister algebra generated by this alpha gamma such that this matrix is unitary. And on this matrix, we have an action of circle group. And this action is basically, so the way this action is defined is actually, so first of all, this U is, I mean, let's say if we know what is braided SUQ2, then after knowing that this U should be a representation of braided SUQ2, the fundamental representation. Now, the way this action is defined, so what we have to do here is that we have to equip C2, two-dimensional, Hilbert space, by an action of the circle group. So what one can do is one can do in many ways. So in this case, I think the action is that if you fix the eigenbasis, the first basis vector, E1, E2, then E1 has degree 1 and E2 has degree 0, which makes E11 degree 0. Diagonals are degree 0 anyway. So that is, that is reflected here, that alpha and alpha star, they are degree 0 elements, degree 0. But this E12, that has degree 1. Now you want U to be actually invariant for this action with respect, circle action. So in order to cancel that 1, you actually have to make this gamma star of degree -1. And similarly here, E21 has degree -1, so gamma has degree 1. So this is just some like if you just write down U as E11 tensor alpha and so on and so forth, and if you just fix the degree on E11, that will dictate what should be the degree of this alpha and gamma.
Now, correct me if I'm wrong, but it seems to me that this coaction is different from the coaction you get when you view U1 as a subgroup of SUQ2.
Yes, right? That's precisely. That is, if you consider S1 as a subgroup, you don't get this coaction, and that is why these coactions are somehow, I like to view them as, highly external. It's not at all present in the data, in a sense. It's there, but not explicitly.
Yeah.
So, and then this pair becomes a system, an object in the category, and then the co-multiplication map is defined by these two formula. So again, like you replace alpha tensor alpha by J1 alpha, J2 alpha, and so on and so forth, and the same formula works. And most importantly, actually, if you have any compact matrix pseudo group, and if you want to define something braided in the similar context, of course, this is not completely true. Mathematically, this statement is not true. But if you if you work with the circle action, then the usual co-multiplication map, that delta uij is uik box tensor ukj, you have to simply replace them by J1 and J2 respectively, and then this formula works actually in most of the time. And we will see one such example anyway today. So this is just an example of a braided quantum group, and this is actually an example of the representation, and this is the fundamental representation for SUQ2. Okay, now let me just go to the topic. Let me focus on the topic of today's talk anyway. So what we are going to define is, we are going to talk about braided, free unitary quantum group, the braided analog of that. Because this universal object of, the graph system, when we are going to compute the quantum symmetry, braided quantum symmetry of graph sister algebra, that comes as a quotient of some quantum group, and that quantum group in the ordinary case is the unitary quantum group. So we want an analog of that, and that was something from the perspective of braided quantum group, that is actually, I feel that is really important by its own right, because that requires some nice, that requires really the fundamental idea of contragradient actually. So this is the definition of unbraided. In the unbraided case, the free unitary quantum group, just to present. So it says that, okay, it is generated by the fundamental unitary is unitary, and its contragradient is equivalent to a unitary representation. That's what this two description says. And then the co-multiplication map is defined the way, which is like dualizing the multiplication of matrix, dualizing matrix multiplication. Now what we have to do is, we have to construct a braided analog of this. Now, in order to do that, we need two actually things in our context. The first thing is the candidate of contragradient in the braided setting, and the second thing is this F, because in the ordinary case, this F is actually an intertwiner. In the braided setting, you have to be careful, because your F has to be a morphism in the category. That means your F has to be your F should have a fixed degree. It should be a homogeneous element. If not, then there will be a degree mismatch actually in the equation. So for that matter, what we actually showed, that if we have a representation, of course, representation of a braided compact quantum group on a Hilbert space, then we can actually construct the contragradient. We can canonically construct a representation which is actually a representation on the conjugate Hilbert space, and that is actually there the zeta factor comes in the play, comes in the picture. And of course, if zeta is 1, then you actually recover the ordinary definition of contour gradient, the definition of the contour gradient representation. And the second thing is, as I said, like this intertwiner, we cannot actually allow any invertible map. We have to allow some specific type of invertible maps, and that actually leads us to something called admissible matrix. So we call a matrix is admissible if invertible matrix is admissible if we actually have, for a given n tuple d1 d2 dn, like they are integers, and there exists another n tuple and this fixed d such that this equation holds true. This whole idea means that your f actually, so if you just forget about the second part, if you just consider this fij equals to 0, when if di prime plus dj is not 0, not d, which means that if okay, so let me just slightly go back. So here we want to actually make sense of this equation. So we have a candidate for u bar, by the way, that we have. Now the next thing is we need to take care of this f. Now not only just we need to take care of this f, we have to take care of this f in such a way that when we apply the circle action on this, it should be invariant. It should not, otherwise it will not be a representation anymore. So because of that, if f and f inverse, if f has degree d, then f inverse will actually have degree minus d. So in that sense, they will actually compensate in a sense. So, and that is some I will say some routine computation which actually gives you this formula which we did in our preprint. So yeah. And now the question is whether such admissible matrix exists, and fortunately it does. For identity matrix, one can always do this. So for identity matrix, you can fix any tuple and then you can choose the other tuple to be minus of d1, minus of d2, or minus of dn, and you can choose your d to be 0, for instance. And by the way, this is true for any diagonal matrix, and in our context, we will be working with diagonal matrix only. But it is also true that there are admissible non-diagonal matrices as well, for which you can actually get something similar.
Can you give some examples, say 2 by 2?
Oh, I don't have any example on the top of my head, but if you want to construct braided free unitary quantum group, there actually this admissible non-diagonal matrix actually comes naturally.
Okay.
So the fundamental difference between braided free unitary quantum group and braided orthogonal quantum group is that you cannot straight away force that your matrix entries are self-adjoint, because if you do, then the circle action will become either trivial, or actually it will be just multiplying by -1 because of that. So the passage from free unitary to free orthogonal requires some work, and that work is actually done by this non-diagonal admissible matrices.
And could you perhaps shed some light of why working with GLN-C you require a condition over the integers?
That is because our Hilbert space. If you look at the definition of representation of a braided quantum group, so the data is circle group has to act on the Hilbert space first, which means once it acts, you can actually fix an eigenbasis, and that means your basis will be like EI. If you look at the circle action on this will be z power some integer EI. So your basis vector, eigenbasis actually becomes homogeneous elements with integer degree. Because of that, we actually stick to integers.
Can you say it in different words that it's because of a Z grading, because you have a T-sister algebra?
Yeah, exactly.
Okay.
Precisely that.
Okay.
Precisely that. Yes.
Okay, I'm so happy. Yeah.
Yeah. Okay, and once we have this, then we can actually define the braided free unitary quantum group, the definition. So it's a C-star algebra generated by Uij and this modified contragradient, and we claim this contragradient should be equivalent to some unitary representation. So that means there should exist some, I mean, for a, like this F is admissible such that F U Z bar zeta F inverse is unitary. And once we have this, then we can actually check that this Uij is actually indeed a homogeneous element of degree dj minus di. And then finally, we can actually also check that there exists a co-multiplication map, which is just replacing the co-multiplication map for the ordinary free unitary quantum group, but you replace U1 IK tensor UKJ by this J1 and J2. That's all. So yeah, I mean, this universal property actually ensures that these two maps exist. And then then there is actually something. So then the next thing is to check that this delta is co-associative, but co-associativity is quite straightforward from the formula.
Sorry, SUTANU, please forgive me, but I think you have a typo here, right?
Yes, could be. Where?
Here.
Oh, okay. Yeah.
One parenthesis missing.
Yeah, you're right.
Okay.
So I think, yeah, regarding this parenthesis, then I think there was another typo in the first slide actually.
Aha.
I mean, since you pointed this out, so here there should be a parenthesis. Yeah.
Okay, so you have three typos to correct. One sheet and two parentheses.
Yes.
Okay.
Okay, let me just. Okay, so now with this three, this triple, like this C-star algebra, this rho and delta. If we take this triple, then we can actually check that this is a braided compact quantum group, and this has the expected universal property, meaning that if we have any braided compact quantum group acting on a finite dimensional Hilbert space, then such that the contragradient is equivalent to a unitary representation, then there exists a map, which is compatible with the co-multiplication map, which intertwines with the respective co-multiplication maps and which sends U to V. This is the expected universal property for braided free unitary quantum group. And this is something we are going to use it as a black box to construct in order to show that the universal object of graph C-star algebra, the braided quantum symmetry group of graph C-star algebra in a suitable sense do exist. So we will show that the resulting object will be a quotient of this. Okay, so now let's get into the main part of the talk. So this is just let me recall the definition of graph C-star algebra. So of course, as I'm pretty new in this subject, so there may be silly mistakes in the definition. I hope not, but still, if you notice, do let me know. So it's basically a C-star algebra generated by projections and isometries, and the conditions are actually reflecting the property of the graph. So yeah, and we are, in our construction, we are going to consider graphs with directed graph with no sink. So
wow, why no sink?
Just to avoid difficulties, probably.
But that's very strong assumption.
Yes, I agree, but yeah, So, okay, in this part, I think I was suggested by my co-author Somallo that for the moment, let's do it without sinks. I said, okay, fine. But then probably
I know life is much simpler without sinks, but it's also much more boring. So.
Yeah, I agree. I mean, as far as I can understand, I also agree, but probably one can relax this condition, I hope. But but yeah, I have not given any much. I mean, I have not tried so far.
It's better to assume too much than too little. That's definitely true.
Fortunately, I mean, the reason is, I mean, as you probably know that it already covers a large class. So I mean, significantly large class.
Yeah,
so okay. Now what we are going to do is, of course, a graph sister algebra canonically admit a gauge action of, I mean, gauge action or the action of the circle group. But here we are actually going to consider something which is known as generalized gauge action. So yeah, so we fix, I mean, our graph is finite. So we fix this like n tuple, this another typo?
Yes. No, it's okay.
Okay. So okay, so this is an n tuple we fix, and then we actually show that okay, this action is, I mean, on the graph sister algebra is on projections. It is identity, of course, because if you want to have a circle action on projections, then it can be either identity or you multiply it by -1 by just negative. I mean, some, yeah. And then on the partial isometries, I mean, you actually declare this S of Sj or S of Ej is an element of degree Dj. So in case of gauge action, then actually we have the D1 equal to D2 up to Dn, and all of them are same. But in this context, we are actually manipulating this grading. So instead of declaring all the elements of same homogeneous degree, we actually say, okay, each of them are different. I mean, of course, we are not here assuming that D1 is not equal to D2 or anything. But if that happens, that is possible. This particular choice leaves some room for that.
It's very reminiscent of defining length spaces in classical topology. Right, this is exactly what you are doing. Instead of having visual circle action, you tweak it by saying that on different coordinates, it rescales them by different powers of a unitary number.
I see.
That's very much in that spirit. And I don't remember. Maybe somebody in the audience remembers that in fact quantum length spaces, which are graph sister algebras, and they do come from quantum spheres that are also graph sister algebras. They also might be defined by such generalized gauge actions, but I'm not 100% certain.
Okay.
How much do you remember?
I don't remember. Probably it is true.
Yeah.
Okay. No, I didn't know that. Thank you for the remark. I mean, I will have a look. But yeah, so far
I mean, think about Wojtek Szymański, Tomek Brzeziński, Sophie Emma. She was Mikkelsen. I don't remember her current surname, and unfortunately, and yeah. So then you find these papers. It's actually very tough. What's happening for quantum length spaces and realizing all of quantum length spaces, graph sister algebras, is actually quite a lot of sophisticated work.
Okay. Thanks for the remark. I will. Thank you. Okay, so yeah. I mean, now using these relations, we can check that this action actually indeed lives to the whole algebra. So, and it's a continuous action. So therefore, we actually can view a graph sister algebra as an object as a T sister algebra with respect to this generalized gauge action. So okay, once we have that, the next thing is in the context of quantum symmetry, you want to fix a state. I mean, in a sense, you want to preserve some finite measure, I mean, on your non-commutative space, so that you actually land up in the compact setting. So that is something, some standard assumption. So far it has been. And now the question is on the graph sister algebra, which state to preserve. And so this was something which Somal and Joardar and Mondal, they have considered in their paper where they have computed the quantum symmetry of graph sister algebras in the ordinary setting for this how do they call it, inverse temperature, I think. Yeah. So they actually showed that if we have a finite directed graph without sinks, then the graph sister algebra, there is a KMS state. Actually, it's KMS log rho d state, actually they call it. And this d is the vertex matrix for the graph, and rho d is basically is of course the spectral radius for this. And what they showed is that this KMS state, there exists a KMS state if and only if this rho of d is an eigenvalue for the vertex matrix, and so if for the rho d eigenvalue there is an eigenvector with all entries are non-negative. This is something they already proved. And so this is of course not, and this clearly says that, okay, we are not actually even considering all graph sister algebras. We are actually considering graph sister algebras where this state, we have this state. And this first two parts, they proved it. So they proved that, okay, the corresponding eigenvector will be this row of, I mean, you evaluate the projection, I mean, tau on the projections. And on this S alpha and S beta, this is given by delta alpha beta and then corresponding to this projection. And the only thing in this context which we require, because we also need a state, we need to preserve a state, meaning our braided quantum group should, has to preserve a state. So for that matter, we want, so in the next slide, I think I have written down the definition, what is the meaning of a braided quantum group preserving a state. So for that matter, we first need the state to be invariant for the circle action, because we want this state to be a morphism in the category. So for that matter, if this is invariant, then we can actually take the tensor of this state with other morphisms. Because of that, we first need this state to be invariant, and it turns out that fortunately this state is invariant for the generalized gauge action as well. So basically now what we are going to consider is, we are going to consider the braided quantum symmetry of graph sister algebra with respect, subject to this generalized gauge action and this KMS state. And that is what we are going to compute. Or, I mean, if it exists. I mean, and first of all, in what sense? And if the next question is whether it exists. So before that, we need some more definition. So first of all, for that matter, we need to see what is the meaning of an action of a braided quantum group. So it is again like one can define an action of a braided quantum group on any T C star algebra. But here we are, since we are working with C star T, the graph C star algebra, we are going to define on that only. Yeah, there is a question, please.
Yes, if I could.
Just show yourself, please.
I'm trying, but I cannot. So please come back to the previous slide, if you could. Yes. Could you explain to me why this KMS state is determined uniquely by values on the products S alpha, S beta star?
Because it's basically a basis.
Okay.
Yeah, I mean,
Okay. Okay.
yeah, because yeah.
And it annihilates many elements because this delta alpha beta is a very strong condition. Because as long as alpha and beta are paths ending at the same vertex, that element is non-zero.
Mm-hmm.
And so you have a huge number of basis elements which are annihilated. But this is what traces typically do, or KMS states.
Yeah, it is not a trace.
No, it's not a trace. It's like with the Haar
No,
method.
no.
It's when you look at the Haar functional, it annihilates almost everything, right? But it shows the moment, when you choose the right basis, right? And then you have this nice effect. So yeah, I think this, I mean, correct me if I'm wrong, SUTANU, but I think that this is because
No.
That's basically every basis element is of that form. Not every element of that form is part of a basis. It's quite a subtle function, but the other way around is true. Every basis element is made out of paths that end at the same vertex.
But my question is why this doesn't lead to a contradiction. So what is so special about this right-hand side? Because these are not basic elements. They are elements which are used to produce linear basis.
That's a valid objection, Tomek. But as I said, this KMS state, this formula kills almost everything. And now if you dig into exactly the basis theorem for Levitt-Pav algebras, which is exactly the same as for graph-sister algebras, you can see that all these special cases that you have to remove are gone anyway because you just have zero over there.
Yes, but still,
maybe I'll help.
Yeah,
it's KMS state with respect to certain one parameter group, right?
Yes.
And that's the group. That's the section. You take your action of a circle, lead it to action of R. And this KMS state with respect to this action. And that determines that that gives the effect that it vanishes of diagonal elements.
Yeah. That's
right.
This is a good explanation.
Yeah.
Because in general, you
so
can't see anything.
Yeah, surely. Yeah. But Tomek's question was slightly different of why it is well defined, if I understand you correctly, Tom.
Yes. Yeah, it's hard to convince. I agree, but well, I was also not convinced in the beginning when I.
Is it triviality or is it a deep result?
No. It's actually not that deep. I would say it's just I will say some observation probably.
Yeah, it's an observation.
Okay.
Yeah.
Thank you.
Yeah. Okay. So now, So now we need to talk about an action of a braided quantum group on TC star algebra. So again, these actions will be morphism in this category that I have mentioned in the beginning. So it's a morphism which will be compatible with the co-multiplication map, and it will satisfy the Podlej condition. The braided Podlej condition, I must say, in this context. And the next thing is we want, since our graph sister algebra is not finite dimensional, so we cannot actually uniquely determine the action. So we have to actually look for some simpler for action, and these actions are a bit called linear actions. So you just look at the action on the generators, and on the left hand side and on the right hand side also, you only consider the SIs. So if the action is said to be linear, if you have this, if you can determine by the, so in a sense, you simply view your graph sister algebra as not as span of SI, but for the action at least, it is sufficient to only look into on this SIs. And the next thing is this action, this action eta will preserve tau if tau box identity. Now here in order to talk about tau box identity, I want this tau to be invariant for the circle action. Otherwise, this is not a morphism in the category, so I cannot take the tensor.
Mhm.
So since tau E was invariant for the generalized gauge action, so I can talk about tau box identity, and then you actually just use the usual definition of state preserving action. So you simply want this to be you evaluate that state at that point.
I mean, normally equivariant would be sufficient instead of invariant, but because it's a KMS state, it has values in numbers, which are obviously invariant.
Yeah, exactly, precisely. And then we will say an action is faithful if you take the slice of the action by any invariant functional, and then if it is dense in CG. So these are again these are some standard dictionary from the theory of compact quantum groups, but you just write them down in this category, in the monodal category, instead of the usual category of C-star algebras. Okay, so now the definition of now the symmetry group of the braided symmetry group in this context is actually an universal object in subcategory. So first we fix the object. I mean, fix the object means we fix the graph and we fix the KMS state, and then we define the category where the objects are braided compact quantum group, which acts on graph sister algebra, preserving tau, and the action is linear and faithful. And the morphisms are quantum group homomorphism, but in this case they are braided quantum group homomorphism. So between two objects, there's a morphism if this morphism intertwines the respective actions.
Mm-hmm.
So now this is the category we are interested in. And again, this category is something which you can actually sort of define using from the theory of ordinary compact, quantum symmetry. So the theory of ordinary compact quantum symmetry.
Jakieś jajeczko zostało, nie?
Okay.
Ignore it.
Okay. And now once we have this, then this is our main theorem. The main theorem is the terminal object of this category exists, and this object is called the braided quantum symmetry group of the graph sister algebra. I think I should have also included the action, the generalized gauge action, which I forgot. I'm sorry. And there are so many typos here, so please ignore this. I mean, I think I pasted it from somewhere, and then this thing happened. Sorry about that. So it's basically the universal object of this category. We will call this as braided quantum symmetry group, and that we denote it by automorphism of this triple. So the graph sister algebra, the generalized gauge action, and the KMS state. So this is our main result, and let me just give you the outline of the proof. The outline is quite, I will say quite. So first of all, okay, this is something what I already mentioned. I mean, for alpha beta we have seen this. So in particular, if you choose SI/SJ, SEI and SEJ with that notation. So then this already comes from the theory of the ordinary symmetry of graph sister algebras. Now, using this fact and the KMS condition, we actually produce this matrix F.
Sorry, SUTANU, sorry, I just forgot. What is this D in the denominator?
D is the vertex matrix. Like the ijth entry it counts how many edges between these two vertices. And rho is the
okay. Mm-hmm.
Yeah, and this rho is the spectral radius. So
spectral radius, okay. Mm-hmm.
Right, and now once we have since tau is KMS state, then actually it shows that this F tilde is actually a positive matrix, which is invertible because tau of E on these projections are non-zero, and it's a diagonal matrix because it kills the other because of this delta ij.
Yeah.
So we have a diagonal matrix F tilde, and that is something we are going to use for the braided free unitary quantum group, this F tilde. And since it is diagonal, therefore it is admissible for any tuple.
Yes.
So, okay. And now some computation actually, I mean, we have done some I will say some standard computation. I mean, using the linearity and everything, one can show that if G is a braided quantum group that acts on graph system algebra linearly and preserves the state, then this is a quotient of this universal braided free unitary quantum group, the C-star algebra, quotient of this C-star algebra, but with F inverse. And where this F is again diagonal, and this F is actually F star F. I mean, which appears in the square root actually.
So kind of say square root of this F tilde.
Yes, square root actually. I mean, it's too much notation for simple square root, but yeah, it's square root of F. So it's again diagonal, and everything is I mean, nice. Now, in order to prove that in order to prove this terminal object, we actually consider some auxiliary category, because see, what we have is that we have, if we have an object here, then that is this C of G is a quotient of this. A quotient of this of the C-star algebra corresponding to the braided free unitary quantum group F inverse. I mean, corresponding to F inverse. Now, this means that we have some generators and relations for this. And if the action is, I mean, now since we are considering this to be an object in this category, that means that the action is faithful, meaning the matrix coefficients for this action generates the underlying C-star algebra. So now we have to prove some sort of universal property for those elements. So in order to do that, what we did is we actually considered some auxiliary, a category. So it is basically, I mean, it's in a sense that initial object, I mean, we want to prove the terminal object as the quantum symmetry. So it is sufficient to prove the initial object of this category. So we are going to construct the universal object in this, I mean, by constructing actually the initial object in this category. So, and by the way, this is again, like, the idea is actually comes from the theory of ordinary quantum symmetry group. The only concern here is that you have to take care of the circle action and T equivariance and everything. That's the only concern. So, but again, but this is, as I said, this is not something, I mean, quite out of the box, because if you just write down the generators and relations for this C-star algebra, you can guess why actually you want this category to be defined like this. The objects are C-star algebras generated by n square elements satisfying these conditions, that this matrix and this matrix are unitary, and morphisms are okay. So this is the object, and rho of X is a morphism. Oh, wait. Yeah. So this is actually yeah. So X is a C-star algebra generated by this Tij. Rho X is the action, and morphism is, and this eta X is a morphism, which is, so if view this X as if a braided quantum group, then this is basically something like this X actually is acting on C-star of E. And this action is, in a sense, this is like a linear action. And the morphism between two objects are precisely like equivariant morphism, which will basically intertwine this eta X and eta Y. So
is your quantum braided symmetry group living in this category C prime E?
We are going to construct the universal object in this category, yes. Okay. And we are going to we are going to construct that object, the braided symmetry group, as the universal initial object in this category.
Okay, and I understand E is a fixed graph, but
yes,
just for this definition, do you still need to assume that it's finite and sync free?
Yes. For this definition, finiteness is required because of this this eta.
Ah, yes, because Ij is okay.
Yeah.
I got you here.
But
yes.
But for this definition, I don't think sync free is necessary.
Okay.
For this definition.
Okay. Thank you. Mm-hmm.
Okay, and then basically what we have is just recall. I'm just recalling the definition of this this universal sister algebra. And now let's consider this is an object in this C prime E. Then if you look at this, look at the generators and relations, you can actually check that by the universal property of this U plus zeta F inverse, there exists a surjective map because this X is acting, I mean, X is generated by 3ij. So this is the whole sister algebra. There is a surjective map which maps Uij to Fii, Tij, Fjj inverse. So that's how this map is, the existence of this map is given by the universal property. Now what we are going to do is, we are going to consider the intersection of the kernel of these maps for every object in this category. Now, this kernel is actually T invariant and it is actually close two-sided ideal. The reason why it is T invariant, because you see that this pi x preserves the degree. The degree of Uij is dj minus di, and you can actually compute the degree of Tij using this equivariance of this tau x, by the way. Because see, eta x is a morphism. So degree of Sj is dj. And now the right hand side, you want the degree to be also dj. Now degree of Si is di. So that forces for each term, degree of Tij is dj minus di.
Yeah, exactly.
So that's how you can determine the degree of Tij. And then this map actually shows that this map actually is equivariant. It preserves the degree. So if you take the intersection of the kernel, then actually what you get is a two-sided ideal, star ideal, closed star ideal. And then you can consider the quotient map. And this quotient space is the candidate of the underlying sister algebra of the braided symmetry group. So you simply take the image of Uij in the quotient, and then actually you can actually check, because this verification actually purely depends on Uij. So you can check this map, actually they are well defined and they do exist, and this triple, so that this U becomes an object in this C prime E.
Now, SUTANU, please correct me if I'm wrong, but
yes,
it seems to me that this universal part, I mean, this CU plus zeta F inverse, that can be very much the same for many different graphs, E. But when you consider all these pi x's and the intersection of our kernels, this is where a lot of additional information about what actually your graph E is comes in. Am I right?
Yes. Okay. Precisely.
Okay, great.
Precisely. And then actually we actually compute, we actually get an initial object that requires, by the way, some more or less, I mean, following this line of arguments, one can easily show that this is actually the universal initial object, initial object of the C prime E. Now, once we have this, then what we can do is we can talk about U box U, and then we can make this an object in C prime E. And once we make this as C prime E, then by using the universal property of U, we can show that there exists a co-multiplication map, which exactly the way you want it to look like. It actually acts on Uij as Uik, Ukj, and you actually have J1 and J2. And then you can show this is co-associativity is more or less obvious from the definition. And by simplifiability requires some work, but that is also not well, it's doable, but it requires some little bit of work.
This by simplifiable is this existence of the antipode condition, basically, right?
Well, I will. Yes, in the ordinary setting, yes.
Okay. Yeah.
Now we actually call this triple as GE, and this GE by construction it acts linearly faithfully on C star of E, and it preserves tau E, and this and the action is given by this eta U. Now if we have once we have up to this, I mean, if we have this, then the rest of the thing is quite straightforward. I mean, actually, the whole the crux of this crux of this whole argument is to actually produce the initial object of this C prime E category. So now, if you take any object in our original category, I mean, where we want to prove the terminal object, I mean, where we want to prove the existence of the terminal object. So if we take any object there, then this triple becomes an object in this category C prime E. The way we have seen, I mean, the way we have actually started with this C U zeta F inverse plus F inverse. And since it's an object in this category, C prime E, then by the universal property of GE, we have a unique map from CGE to CG, which actually will intertwine these two maps. And this is equivalent of saying that G is actually is the terminal object in this category. So that's how we prove the existence. And as you have noticed that this without the existence of braided free unitary quantum group, we couldn't have done that actually. Yeah. So that's how we prove the existence of the universal terminal object. And by the way, one more thing which I deliberately suppressed in the whole talk. In this construction, there are many places where we have actually used the bosonization of the braided free unitary quantum group. So the thing is, it's actually something maybe I can just mention pretty quickly. So this braided action. So if we have an action of a braided quantum group on graph sister algebra, you know, if you know, like for braided Hopf algebra, there is something called bosonization, which is an ordinary Hopf algebra. Then you can always induce an action of the bosonization of G on the C star E. So at many places, we actually pass to the bosonization because bosonization is an ordinary compact quantum group, and you have used some of the results related to the ordinary compact quantum group, and then we actually somehow thrown away the circle part from the bosonization. That is roughly we have done, but for this computation, it seems the bosonization, the contribution from the bosonization was not that big. It was more pretty conceptual, and basically you have to, I mean, you know, go through all the definitions and stuff, manipulation, of course, and taking care of the homogeneous elements and commutation relations and everything. Anyway, so that's the existence. And now finally, let me just so this is what actually completes the proof. I mean, the outline of the proof that the braided quantum symmetry group for a graph sister algebra exists. And now, once this object exists, then again you can say, okay, this is a braided compact quantum group. Therefore, you can consider the bosonization of this universal object. Question is whether that bosonization can be interpreted, because bosonization is an ordinary compact quantum group. Question is, can you interpret that as a symmetric group of something? In this context, the canonical choice will be, you have a circle action on the graph sister algebra, induce the corresponding integer action, and take the cross product. So cross product will be an unital sister algebra. Question is whether the quantum symmetry group of the cross product coincides with the bosonization of this braided of this universal object. So far, we could prove that, but what we have is that the bosonization acts on the cross product. But we could show that whether that is the universal object of the cross, I mean, symmetry of the cross product, because this is something, you know, like quantum symmetry of the cross product, computing quantum symmetry of the cross product in terms of its factors, quantum symmetry of its factors are pretty interesting problem, of course, and these results are known, I think, case by cases, but not in complete generality. So yeah, this is something we tried, but even for graph sister algebra, we couldn't do. I mean, we couldn't go further, to be honest.
Sorry,
And now,
could you
yes.
back off one slide? I would like to see again what this script U is. Where do you define the script U?
Here.
Ah, great. Yes, that's this quotient. Okay, thank you. Just double checking. Thank you so much. Yes.
Yes. And now as usual, the question is, okay, we have developed a nice theory. Now question is, what about examples? And obviously we computed it for Kunz algebra. So we considered Kunz algebra, which is a graph sister algebra with one vertex and in many loops, edges. And then we equip Kunz algebra with generalized gauge action, which actually comes from the graph sister algebra. Now, what we denote is U zeta plus n. This n actually corresponds to the U zeta plus f, where f is the identity matrix. So what we first observe is that the braided free unitary quantum group corresponding to identity matrix canonically acts on ON, and it is, for this generalized gauge action. And now for the Kunz algebra, the vertex matrix is just, 1 by 1 matrix which has n, that has n many edges. So spectral radius is n, and therefore the KMS state is pretty straightforward. It is 1 by n delta, and therefore this f tilde is just identity matrix. So now the question is, this un plus id n, un plus un zeta plus acts on ON. Question is, whether this is the universal object, and yes, it is expected that this proof actually is slightly, it requires some work. It doesn't follow from the known results, because this, when you generate this Kunz algebra, it is not like, it's not finite dimension. You have this degree 2, degree 3, degree 4 terms, and so on and so forth, and you have these relations. You have to take them into account. So we had to prove the universality, this part actually, considering case by case products, different type of generators, products, and so on and so forth. And yeah, so this proves that the braided quantum symmetry group for the Kunz algebra is basically the braided free unitary quantum group for the identity matrix. And now, if zeta is 1, then you actually recover the unbraided result. The result that is actually known for in the unbraided setting. So the braided, the automorphism group for the Kunz algebra is isomorphic to UN plus. So yeah, so this is basically what we have done together so far, and then we are trying to see whether we can, for instance, remove the hypothesis. We discussed about this, not that's probably that seriously, but yes, I think we should try to see whether we can remove this graph with no sink condition. That is something which is probably worth looking at. Yeah. And then other examples. My original motivation to consider this thing, actually, they actually follow from these results. For instance, if I want to compute the braided symmetry for matrix algebra and so on and so forth, they actually more or less follow. So probably follow from here. I have not verified them separately, but yeah.
And do you have any other examples? Like, how about SUTANU graph sister algebra?
No. So far, we have not computed anything apart from this. That's a shame, but yes.
I'm just trying to understand. This is a bit confusing to me. When I have a graph, whatever assumptions, I have just a graph, and I have its graph sister algebra, and I'm looking at its symmetries in whatever sense. There is intrinsically no braiding associated with a graph.
No. This is an external data.
External data. Okay.
So in a sense, I try to look at it in the following way. So if you want to compute the symmetry of cross product, then it is not that easy to even get a compact quantum group, genuine compact quantum group, which acts on the cross product. So in this way, if you proceed through this braided symmetry, then this the point is this braided tensor product. This already captures the information of the circle, captures the information of the action of the circle group. So essentially, the resulting object, the symmetry in the braided sense, that itself captures the symmetry of the graph, as well as it captures the information of the circle action.
Okay, that's a very good answer. This is exactly what I
that
wanted.
is what
Yes,
that is what I would like to see in that way. So it's a single object which captures the symmetry of the cross product up to a certain extent, if not completely. Yes, how much?
So it's not just a symmetry of a graph sister algebra, but the symmetry of a circle graph sister algebra.
Yes, if you prefer.
Yeah,
Yes.
Tomek?
I have a question about in the very same spirit. Maybe stupid question. What happens if you consider the usual gauge action on the graph?
Yes. Algebra? So yeah, that's a very good question, I will say, because why not? The reason is, if you take the usual gauge action, let me just go back to this here. So just first of all, look at the action of the circle action on the Uij. If you take the usual gauge action, then this action becomes trivial.
Yes, I see.
And then you don't actually. So if you take the usual gauge action, you will get the ordinary quantum symmetry group. If you take zeta to be 1, then also you get the ordinary symmetry group. So yeah,
that's identity, right?
Sorry?
F becomes the identity matrix.
No, in this context, F is not identity.
No, but for the usual gauge action, no?
For the usual gauge action, actually this F in this context, this F depends on the where is it? So F depends on actually on the
KMS state. Okay.
KMS state.
Yes, of course.
So F is responsible for this change of basis actually for the contragradient representation. So yeah. So for instance, also in the last example, I mean in the Kunz algebra example, F is identity, but still we have a non-trivial braided, I mean genuine braided compact quantum group. So yeah. So if identity also doesn't mean that And by the way, I mean this is not a part of, and this is something which is not a part of this talk. So this braided symmetry of graphs, not graph sister algebra. Graphs are highly studied. Now, if you take a finite graph, then the question is, in the usual ordinary setting, you have the symmetry is a quotient of the quantum permutation group. Now, the question is what happens in the braided setting. So we already have something which is called a braided quantum permutation group, which we call anionic, because on finite space we cannot consider circle action. We have to consider Zn or something like that. So because of that, we call them anionic, because they actually satisfy this anionic relation. So, but surprisingly, when we try to compute the symmetry of finite graphs, we don't get anything non-trivial, I mean braided. So from that perspective, I think, of course, ordinary symmetry is nicely behaved with the graph, symmetry of graphs, but braided symmetry is not nicely behaved with the symmetry of the graph, but for the graph sister algebra. And as you can probably guess by now, that braided symmetry is more non-commutative by nature, I would say. Yeah, Thomas, please.
I have a question about this additional symmetry. Given a graph, how could you classify all these T actions compatible with this presentation, graph presentation of this algebra?
So our T action is already quite, if you know SI, then you actually, in a sense, you can say this action is defined in an ad hoc way. We don't have any restriction on D1 or DIs actually. So you can pick any DI and still it will work. But
so you can fix this DIs freely.
Yeah.
There are no conditions.
No.
Okay.
No conditions.
Thank you.
But yeah, if you change your I mean, for instance, as you mentioned, that if all the DIs are same, or even all the DIs are actually 1, then you get ordinary. So if you vary your DI, you will get different type of objects, I will say.
Mm-hmm.
And these different DIs, different choice of DIs will change the braiding, right?
Yes. That changes the braiding, and that changes the degree of this UIJs actually.
Yes.
So the degree of UIJ is DJ minus DI. So if you change DI DJ, then that will change the the braiding.
Mm-hmm.
And one more thing is remark is regarding this quantum permutation group. So you know that if you have 3 points,
Yes.
then the permutation group is classical.
Yes.
But in the braided setting, we have something non-trivial. The underlying sister algebra is commutative, but the co-multiplication takes value in non-commutative tensor product. So in a sense, this braided quantum permutation group on 3 points is inner commutative, outer non-commutative.
Mm-hmm.
And by the way, this is not surprising, because to the best of my knowledge, the first example of a braided quantum group in the sister algebraic setting I have seen in the locally compact case by Voronovich. And in the example that he considered, that was commutative, by the way. The sister algebra was commutative, but the co-multiplication map was non-commutative.
Mm-hmm.
So that is not surprising, because that was already known. But in the quantum permutation group, we also observed that. So yeah.
Mm-hmm.
But yeah, I mean, as far as this talk is concerned, I think that was my last slide. So thank you for your.
Okay, thank you very much.
Hello.
Okay, great. Now we can proceed with further questions, if any. Richard, you seem to be eager to ask.
So can I ask, out of
Yes.
curiosity, instead of having DIs, you could just subdivide your edges and use standard gauge action, couldn't you?
Could you
just subdivide your edges into so edge, edge, subdivide into, yeah, just write down, yeah, precisely. Now your DI is 1 plus 1, right?
Yeah.
So now your DI is 2 between the initial and final point.
Mm-hmm.
Yes.
But otherwise, everything is more or less the same.
Yes.
It looks plausible.
Yes,
I'm just curious whether you can just replace everything by standard gauge action, where you increase your metrics, right? You add all these vertices with valence 2, which somehow sister algebraically don't do anything.
Yeah, you are right. So right? I think yes, I think you are right. And again, as I said in the beginning, the article that I saw yesterday by Neshviev and Eric. So I think it is possible to, if you can somehow give meaning to the transmutation, because they consider transmutation for quantum groups. But if you can somehow define transmutation of sister algebras, I mean, not Riefel deformation, but transmutation, because these actions are, some coming from external data. So probably whatever you are saying, that is possible, because transmutation means if you have a compact quantum group, then you can construct something which is braided. The sister algebra remains, I think, underlying sister algebra remains isomorphic. The only change is happening in the co-multiplication map. So yes, I think whatever you are suggesting might be plausible if something of that sort, in general, if that's a type of mechanism can be developed.
I'm just curious.
But you see, Richard, you get here a different sister algebra. I mean, you change the graph, and it changes the graph sister algebra. So yes, you switch into the gauge action, not the fancy action, but for a different sister algebra.
So how much do you change with sister algebra?
Well, I mean, just take, I know there is a sink, okay? But okay, so maybe let's try to do it without sinks. So I have just the circle algebra. I have one edge, and now I subdivide it.
Mm-hmm.
Okay, so I change from the commutative sister algebra of C of S1 to 2 by 2 matrices tensored with C of S1.
Sure. So it's Morita equivalent. Right?
Yeah, it's Morita. You're right. Yes, I think that's what would happen. Yes, okay.
So you can just stabilize the thing and then it's invariant.
Yeah. Now I'm happy, Ryszard. Yes. Yeah.
Okay.
Jacek.
Yes.
Hello, Glasgow.
Hello.
Thank you for the talk. I wanted to ask two questions. Maybe first about, you mentioned the quantum permutation group on 3 points, braided quantum, which is, well, this algebra is commutative, since product is non-commutative. Is the sister algebra finite dimensional?
Yeah, it's actually isomorphic to C of S3. So yes.
Okay. And the second question, are there examples of braided quantum groups where the braiding is not over circle or integers, something else?
Not I'm aware of.
Okay, so something, taking something simple, like, I don't know, products or...
No. Yeah. So you have to, the reason, we are so far stick to the circle group because it's easy. And there is a natural, because it's commutative, co-commutative, and there is a natural, because if you take an abelian group, then any bicharacter is an R matrix, unitary R matrix. So you can use that fact actually. So, but if you pass to non-abelian groups, then probably you can have R matrix, but that may not be unitary. So for that matter, I think what you have to do is you have to consider the Jeter-Drinfeld category, what I think Ryszard and Christian, they developed. And so you have to first consider the category, representation category or action category, not over a quantum group, but over the Jeter-Drinfeld quantum double of the quantum group. So, but answering to your question, no. I'm not aware of in sister algebraic setting. I'm not aware of any other. Any example of braided quantum group where the ambient quantum group is actually a genuine quantum group.
Okay, thank you.
May I ask one more question?
Yes, sure.
So what happens when you vary zeta? Your parameter.
Yeah. What if it's a root of unity?
The root of unity is allowed. But
one is
root
allowed,
of unity,
right?
No. But even in primitive root of unity is also allowed. But but how these groups depend on zeta? Yeah, that's an interesting question. I don't know. We have never thought about it.
Okay, thank you. Thank you for a nice talk, by the way.
Yeah, very nice, very nice. Anybody else? Mark? No? Lech? Okay, I don't see any raised hand. Manish, you know? No? Okay.
Sorry, I had my microphone switched off. Well, okay. I have no essential remarks that maybe somewhere later I will take something. So I will give some remarks to the author.
Okay.
Not at the moment.
Okay, good. So in this case, let me have a question. So first, but it was actually already Jacek's question. When you look at this generalized circle action on a graph sister algebra, you just can have a Tn action of a torus. That's exactly how you do gauge action for higher rank graph sister algebras, where for every color of your edge, you have to choose a different circle. So then you'd still have a commutative sister algebra, an abelian group, just an n torus. And I suppose not much would have changed. And instead of just simple unitary zeta, your braiding would be determined by some nice
matrix.
of zetas, very much like you do non-commutative higher rank torus, as Mark was doing. Yeah.
Yes.
And I guess everything would go very much the same way, right? I don't
more or less. Yes.
Okay.
Yes.
Okay. Good. So this was just a warm-up. But now a serious question. We've been working for some time on factoriality of graph sister algebras, and factoriality both in the covariant and contravariant sense. So we very much digged into what are conditions on morphisms of graphs, so that you can have either covariant or contravariant induction for star homomorphisms between the graph sister algebras. And now I'm wondering if we have here something similar with this symmetry. I understand my question is far-fetched because you have much more data here, but I'm pretty sure that my question could be refined to a genuine concrete math question. I'm just wondering if you would have some kind of a morphism which would respect all the additional structures. I don't know, you have some KMS states, whatnots. Then would it induce also a morphism between these quantum or braided quantum symmetry groups? Do you think that it's plausible? I mean, it's a very simple-minded question. Maybe let me draw it. I have a graph E, finite, no things. I have a graph F, finite, no things. And here, for me, you produced some UE, and you produced for me some UF. And I think basically your claim is stronger than the way you formulated it, because you didn't just prove existence, you basically constructed it. And this is far more beautiful. And now, you know, we study morphisms here. Okay, that's a very, very delicate and complicated issue. So that we have factorial induction between graph sister algebras. And now I am wondering if I can somehow, you know, complete the diagram. Here I have some associations, and here's a big question mark, right? Could I have, for an appropriate, maybe it would put additional conditions on, I'm pretty certain it would put additional conditions on the morphism of graphs, whatever it means here, right? And it's also not clear whether it would be covariant or contravariant. That's because we have it both ways. We have different conditions for covariant induction, and we have different conditions for contravariant induction. Okay, so in other words, so here what is done, I mean, here I have my graph C-star algebra C star of E. So on objects, it's absolutely obvious what happens, okay? And so it has C star of E and C star of F, okay? Capital F. Sorry, I'm writing with a mouse. That's why it's not.
Yeah, it's okay.
And now here we have induction in both ways. We have F pullback, if you will, and we have F push forward. And now these are the usual star homomorphisms, okay? And now, depending whether we want to have the covariant or contravariant induction conditions vary drastically on what this F is, okay? But we have a commutative diagram, okay, in some categorical sense. And now I'm wondering here, you build some, you associate, but you have some more data. It's not just a graph, okay? So it has to be made precise. With some more data added to a graph, you have this braided compact quantum group and this compact quantum, braided compact quantum group. So I'm wondering whether you can complete this diagram the same way we completed just for graph C-star algebra. I don't expect you to give me an answer. I just want to tell me if there is some immediate red flag that it's impossible, is nonsense, or whether it's...
No, I don't know, but I will try. I mean, I will, if I want to do it, I will maybe try to do it for unbraided case first.
Yes.
Is it known in the unbraided case?
Yeah. No, nothing is known. Zero. I mean.
Okay.
I think no, nobody studied the factoriality of this symmetry, right?
Okay.
Tomek?
So
people studied this.
Oh.
Okay.
In the context of Galois theory.
Oh.
But this is factorial with respect to very restrictive class of morphisms. For instance, if your morphisms are invertible, but I suppose in your case, invertible morphism in your sense are fairly trivial. Please correct me if I'm wrong.
Well, it again depends whether you speak covariant or contravariant. When you have covariant association, you have far more freedom, but
Yes.
probably yes. If you demand some kind of bijectivity, it might go very wrong. But I'm not certain that it becomes trivial. No, not at all. And typically, you must have things are finite to one or injective. You must be injective on vertices. So I mean, that's not so far from being bijective.
Yeah, the point is that even classically, such a question has very little chance for getting some interesting answer. But there's another possibility.
Okay.
Instead of consider, if you have morphisms between graphs or morphism between sister algebras, you can think about automorphisms of these morphisms, which means the relative situation.
Wow.
One, if you have a graph with some fixed map or morphism to some other graph, or some sister algebra with some homomorphism to some other algebra, you could look for a universal algebra of this morphism. So think this, I think, could give some interesting results.
Okay.
I do have a bit different suggestion, if I may.
Sure.
So so instead of morphisms, think of correspondences. So like correspondences between graphs, between groupoids, right? Like Morita equivalent groupoids, things like this. Because you want to keep some of the structure of your graph, right? So think of a correspondence between two different graphs.
So what is the correspondence between graphs? I understand correspondence between graph sister algebras, but between graphs?
By module, well, it's but like another graph, right?
In groupoid situation, it's about the Zakrzewski morphisms.
Yes.
Just another graph, right?
Yes. Okay. Okay. Yeah.
Okay. And then you could think about symmetries of that one as kind of relative symmetry of a situation.
Yes. Yes, I like it. I like it. Okay, if there are no other questions, are there any questions? I don't see. So in this case, let us thank our speaker again. This is a very beautiful talk, really. Thank you so much.
Thank you.
Of course, I'm biased because I'm working on it, but I thoroughly enjoyed it, and I think it was a beautiful presentation. Now, let me stop recording, but please don't go away.